Good afternoon, everyone. We'll get started. I'm Deborah Reeves, the Coordinator of Research Services in the Library. Firstly, on behalf of the Parliament of Victoria and its members, we acknowledge the traditional owners of the land on which we gather today. We pay our respects to them, their culture, their elders past and present, and we also pay our respects to people from First Nations communities who may be joining us. I welcome you to our seminar today about battery and energy storage technologies, which we're presenting jointly with ATSE, the Australian Academy of Technology and Engineering. When we have questions later, I'm getting ahead of myself, but we do have a spare microphone, so please wait for that to arrive before you speak. We are filming this today. Our moderator today is Professor Sandra Kentish, who is Chair of the ATSE Victorian Division Committee, and Redmond Barry, Distinguished Professor at the University of Melbourne. Rightio, I'll hand over to you now, Sandra. Thank you.
Thank you very much, Deborah. And it is a pleasure to welcome you to this presentation. The transformative potential of battery technologies, emerging storage solutions and their impacts on renewable energy, transportation and industry is rapidly evolving. And in this session, we hope to inform you a little bit more about some of those developments in batteries, their applications and impacts in terms of industry efficiency, economic benefits and sustainability. Basically, how ready we are to charge the future. We have two exceptional speakers discussing this topic today. They both have distinguished careers and widely recognised both nationally and internationally as experts in this field. I'll introduce both speakers. So our first speaker is Professor Maria Forsyth, who is Alfred Deakin Professor and Deputy Director of the Institute for Frontier Materials at Deakin University. And I forgot to check this one. She's also an ICOBASC visiting professorial fellow at the University of the Basque Country in Spain. Maria has worked at the forefront of energy materials research for the past 30 years, consistently made breakthrough discoveries with applications including a novel fuel cell design and battery storage. She serves on a number of bodies, including the Future Battery Industry, CRC, the ARC Industrial Transformation Training Centre in Future Energy Storage Technologies, and she's an elected fellow of the Academy, as well as the Australian Academy of Science and the Royal Australian Chemical Institute. Our second speaker is Professor Matthew Hill. He is Deputy Head of Chemical and Biological Engineering at Monash University and also Senior Principal Research Scientist, Manufacturing Division at CSIRO. He's developed a platform technology for a group of materials known as metal organic frameworks. This groundbreaking technology allows smart, selective capture, release, separation and storage of molecules with applications including in energy storage and batteries. Matthew won the 2014 Australian Prime Minister's Prize for Science and the ATSE 2019 Solomon Award for sustainable ability to foster research, industry, collaboration and knowledge translation. So I'm going to hand over to Maria first, then Matthew will speak, and there'll be time for questions afterwards.
Thank you, Sandra. I'm going to take my jacket off. I'm boiling. Sorry. First thing I'm going to do. Thank you very much. It's a real pleasure to be here. And thank you for the introduction. So, see if I can get this to work. Right. So, 30 years I've been working in this field, absolutely, and it's really exciting to see the possibilities now of actually beginning to take that science we've been doing and translate it into real devices that can power our society. So today I want to talk about energy storage technologies, batteries mostly, which can support the transition, but I also want to look at the possibility, or the issues relating to existing technologies. Are they the only ones we have? And are there other technologies that might have a role to play in the future? So first of all, I want to give you some statistics, right? So this is this shows from colleagues in the ICOBASC, in the Basque Country at CRC Gune, Centre for Batteries. This shows a demand that we expect for batteries in general by 2040 at the current rate, and this keeps every year. They keep updating these numbers. They keep growing. 11.6 terawatt hours by 2040. Most of that's going to be around. Let's see if this works. No, it doesn't. Around transportation, electric vehicles, also stationary storage. At the moment, we've got very little in stationary storage, but it's projected to be like 2 terawatt hours, heavy vehicles. And at the moment, most of our batteries are in our laptops, in our phones, in our computers, in our other personal electronics. But we're looking very much at requirement of a lot of batteries, right? That's a lot of batteries. And to put that into context, there are 300 potential gigafactories being built around the world, not yet built. So it's 300 gigawatt hours per year, basically. That's not enough. That won't be enough. right, if we're going to really get by 2040. Lots of potential. So now this is a bit of chemistry. I won't go too much detail in the chemistry, but this is what the battery that we have in our laptop and in our phones and everything else is basically a lithium-ion cell, multiple lithium-ion cells. The reason I'm showing this is to show just how many materials go into that lithium-ion cell. On the left-hand side, you see all the critical minerals and metals we need: lithium, copper, graphite, cobalt, nickel. And then you also have the current collects aluminium, a whole lot of other elements that we dig up out of the ground. And at the moment, we dig it up, we sell it, we ship it off and bring it back as a battery or components of a battery. We can do a lot more than that here in this country. And also I want to show you that even though it's a lithium-ion battery, there are multiple types of lithium-ion batteries. Not all of them are the same, and not all of them should be used for particular applications. Some are safer than others, some are more energy dense than others, and Matthew will talk about some other ones later on today. This is also another slide which I thought was really interesting in terms of the demand versus supply for lithium-ion batteries just for EVs. Forget everything else we want to electrify, all of our stationary storage, just for EVs. By 2035, the light blue is the constraints based on the materials that we currently know in the ground that we can actually, in time, beneficiate and make into materials we need for batteries. And the dark blue is what the demand is projected to be. And you can see we catch up by 2035, but there is a supply shortfall, right? So there's a demand is going to be the lagging, or sort of supply or demand be lagging the demand just for EVs. Doesn't include stationary storage. Then we've got the environmental aspects to think about. And I know I was speaking to Sandra, I think we just have to do it better, that's all. I'm not saying we shouldn't do lithium, I'm saying we must do it better. We must consider the fact that when we're digging things out of the ground, that we do it in a sustainable way, that we do it in a way that, and Europe and other countries are going to demand high ESG. The environmental goals are very high, and the amount of water that's used to be able to clean our copper that's used as current collectors in a battery, the amount of water we need for any mining, the extraction of salars for lithium, all those elements that go into a battery all need to be mined and beneficiated. And so that's a problem which we have to consider, and that just means doing it better. Not that we don't do it, we do it better. Finally, what happens when we use all our batteries? Where do they go, right? We have to do this better as well. So China is not doing badly. They've got multiple recycling companies over there. We've got a couple here in Australia, two in Victoria, trying to set up. But we have to think about recycling. We have to think about using the waste from the battery as our mine, if you like, that we can then reuse the lithium, reuse the cobalt, reuse the nickel, etc. And EU is already regulating that, actually, so there'll be no choice ultimately if you want to sell to EU. Okay, so that's lithium, but there's more than one type of battery, and for the last 100 and something years there's been multiple batteries. I haven't got time to tell you about all those. Lead acid, which we all use in our car, most of us, and that's 95% recycled, by the way. That's been around for 150 years and still much the same. But there's also the periodic table here, and pretty much any element that's on there, you can think about how you can use it to create energy or to store energy. So lots and lots of possibilities up on the top left-hand side and over here also on the right around elements that can be used to make advanced batteries, new batteries. So lithium sulfur is one that we'll hear about later on from Matthew. Flow cells you must have heard about. There's vanadium flow, there's iron flow, there's organic flow, lots of different flow. Queensland is about to build a vanadium redox flow battery and an iron flow battery. They're good, they're big, they're good for slow release, good for when you want to put it for a grid, but they have their problems as well. You also have solid state metal air. Also overseas, people are using metal air batteries where you might have zinc or magnesium or aluminium as one of your elements, and then you use oxygen as your other source of energy. They're also interesting but have their own technical problems that are being resolved at the moment. But there are commercialisation aspects there that are well established. People are making these cells. And sodium-ion batteries are one I'm most passionate about at the moment. It's an area that I've been working in for more than a decade, and I think it's an area that we have opportunities for here in Australia as well. Faradium was the first company to commercialise in 2011 in the UK. They got bought out by Reliance a few years ago now, and India's going to try and make a gigafactory of sodium-ion batteries. The beauty about sodium is it's a bit bigger than lithium. It's near the periodic table, just below lithium. So it's bigger, but it has very similar chemistry. So what we've learned from sodium over the last 30 plus years, we can actually translate into the sodium area. The same gigafactory that makes lithium-ion batteries can make sodium-ion batteries. So that's actually a benefit for going to sodium as well. It is slightly less reactive, so you wouldn't use it in a car that wants to go 1,000 kilometres, but you could use it in a car that maybe is in the city, or a car that's, or other light EVs. Definitely you can use it for storage. And I'll talk about a company in Victoria that's actually importing these for Victoria as demonstrations. But also, sodium batteries have been around for a long time, actually. So the very first ever EV that was released by Ford in 1966 was based on a sodium-sulphur battery, molten sodium of all things, with molten sulphur battery. At 350 degrees Celsius is where it operated at. But they had a couple of fires and they shut down that program. We have fires every day now, right? But back then they had a couple of fires and they stopped electric vehicles basically in 1966. This came out of the Chicago Tribune in 1966. It was very interesting. But late last year, November 2023, sodium-sulphur batteries been installed on a very quite warm site in WA on a mine site. So again, it's being utilised. Everything has its problems and good and bad points, but in this case, stationary storage, high temperatures, not a problem. Why do I passionate about sodium? Because it's actually more sustainable for me than lithium, because sodium is everywhere, it's salt. Sodium ion basically is everywhere. Also, for lithium-ion batteries, the current lithium-ion batteries that we have use graphite as one of the electrodes, the anode. Graphite we have to mine, it's a critical mineral, or we can make it synthetically, which is expensive. But for sodium, you use what's called a hard carbon, different type of carbon, and that you can get from waste, biomass, right? So you can get it from pretty much anything you can burn and make. And we're working with Barwon Water actually here in Victoria to look at biochar and its opportunities for making hard carbons for sodium batteries and also for supercapacitors. And also the materials that you use on the other side don't have to be as critical. They can still be, you still use nickel and iron, but you don't have cobalt in those electric cathodes. And so that's also a more abundant element. So that makes them more sustainable too. It's not either or, by the way. It's not either or. 11.6 terawatt hours by 2040. We're going to need a lot of batteries. It's more the right battery for the right application. For sodium, there's already, the last few years, there's already at least four companies that are out there. Faradion got bought by Reliance, as I said. They partnered with ICM, a venture capital group in Victoria, to set up what's called Nation Energy about a few years ago now, a couple of years ago. And I'll show you in a moment where they've installed their batteries in Victoria and they're trialling them. Hina, Tiamat and CATL, the biggest lithium battery manufacturer in the world, and they've just released about a year or 2 years ago, they showed a video online which said, we can make sodium-ion batteries now, and we're making cars with sodium-ion batteries. And that got the whole world thinking, oh, there's more than just lithium, which because they can use the same gigafactory to make sodium as they make lithium. Tiamat's a French company that, again, colleagues of ours who spun out about 5 years ago, and now at the beginning of this year they have raised a lot of money to make a 5 gigawatt hour production facility in France, which is fantastic for them. They've been making their cells in China otherwise. And then Hina, another colleague from Beijing, they set up Hina, a company which I actually got to ride in that car last year at the Sodium Battery Conference, run by Sodium Ion Battery. And again, gigafactory that's set up to make sodium ion batteries in China. This is Nation Energy, very quickly. I got this from them the other day. They've got 12 demo units around Australia, 6 of them in Victoria, which is fantastic, all of the order of between 10 and 30 kilowatt hours. So they're more small storage, like one of them was on a dairy farm, I think some are in sort of factories are not megawatt hours. But it's a beginning, it's a start, right? And this is demonstrating the fact that we can utilise sodium in certain applications, which I think is really great. However, the complaint that they have is oops, no, it's not what I want to show you. The complaint they have, go back, is, and I had a whole slide on this, but I'll just say it and without showing you all the information, is that they are struggling because all the technologies, all the standards that are written, regulations are around lithium batteries primarily. And so if you bring anything in which is not lithium, you struggle. Even if it's lithium metal, as we'll hear about later, you struggle. The regulations that are there are a problem. We need to try and fix that. And the last thing I want to end up with is we are already manufacturing in Australia. This is Deakin University, where I'm currently at. Our battery hub that was funded by the Victorian Government, the HESI Fund, the Department of Education. We are now making these prototypes. We're actually making bigger ones now. And we're working with companies in Victoria and around Australia to demonstrate their materials and demonstrate the ability to make Australian-made, basically, batteries here in Victoria. And we're hoping to actually grow that capability, and expand it beyond just what we do here. With that, I'm going to hand over to my colleague.
Thanks very much, Maria. And so what we thought we'd do is, Maria's, I hope, blown you away and set the scene of the broader picture. I wanted to do a bit of a case study of what a journey is looking like in Melbourne for taking one of these technologies and trying to bring it to the everyday person. So we have a team. We're out at Monash in Clayton. About 10 years ago, Meinak and myself started working together because we realised we both got out of bed in the morning because we wanted to create jobs and companies and take something that's a nice idea in a lab and put it out. The thing we keep saying is we want it on sale at Bunnings for $19.95. That's our goal with the technology that we're doing. Marduk was our first PhD student. She came to us from Iran. They both speak about 5 languages each, and when we started working in batteries, I said, give me a word from one of your languages that I can say that we could call the company. And Gova is an ancient Persian word that means battery. The modern Persian word for battery is battery, so it wasn't quite there. So that's the name that we've gone for with our technology. Maria talked there about the huge demand that's coming in energy storage. And far be it for us to say here in Australia, we have another problem that is there actually enough minerals in the ground if we keep using the same batteries that we have now to make those same batteries? This is some information from the International Energy Agency, and you can just see in the millions of tonnes of minerals that are currently being used, 3, 4, 5. And if we go ahead and we want to hit our net zero scenario, which I hope we do want to hit, we need a huge amount of minerals. Like, it's off the charts here. And there's a genuine question there of, do we even have them? We probably do, but of course the good resources go away. It becomes more and more expensive. Those environmental challenges go from difficult to insurmountable if we don't have a broad array of technologies that don't draw so much on these critical minerals. And so the battery chemistry that we're interested in is lithium sulfur batteries. So Maria was then talking about lithium ion batteries. There's some combination of nickel, manganese, cobalt, a few other metals in the cathode. And the cheapest you could buy that is $15, $20, $30 a kilo. Well, lithium sulfur battery uses sulfur. It's 25 cents a kilo for that same part of the battery. Sulfur is a waste product. It's everywhere. It's used in car tyres to make them last longer. It comes out of every chemical production process. It's a product that Sandra's developed technology actually removing over the past because it's ubiquitous. And so these batteries have been known since the 60s, and there was a long list of reasons why they don't work. So we thought, what if we could make them work? And that's been our last 10 years to work on this. Because in theory, they should have a higher capacity, maybe ballpark double amount of energy per kilo of battery compared to a lithium-ion battery. And they should be some version of a lot cheaper as well. And so a lot of the time when we talk about this, we get that question, well, how much cheaper? And the challenge we have to think about it here in Victoria is, I'm in the lab making these and I want to build a gigafactory. I'm now doing forecasts to work out how cheap it's going to be. So I never want to say a number, I want to talk about the fundamentals. That's why I talk about it's 25 cents a kilo for the material that goes in it instead of $10. That makes a huge difference when we make a battery out of it. The other thing to reinforce what Maria said is when you think batteries, everyone thinks a lithium-ion battery. We've never only ever had one battery. We've always had 4 or 5 of them. Anyone who drove here today had a lead-acid battery in their car. Lead sounds bad, but we recycle something like 99.9% of batteries. So it's actually not that bad environmentally because it's a closed loop that we're using. And so lithium sulfur is quite interesting to us because it's high performing. You can use it at room temperature, but it has a lot of technical challenges around it. We're now starting to get interesting because people out there in the real world are saying, we think this is the way to go. This is a quote here from the CEO of Stellantis. Stellantis is a group of companies that leading the push into electric vehicles, and they see that the supply chain issues being resolved is a really interesting area. So here's 10 years of my life on one slide as to what does it take to work in this area. So what researchers typically do is start out with these little coin cells, so what's in your watch. And we're making little batteries and we're varying all the components in there and we're sticking them on a machine and charging and discharging them maybe a few hundred times. When we started, we high-fived each other because we got one to charge 10 times. Our record is in the thousands now, and that's 10 years of development. Now, when you talk about trying to get this out to the real world, that's not really relevant to the real world. It's nice for development, But what we need to do is make bigger batteries where how you manufacture it starts to weigh in on the performance of the battery. And a typical size battery is what you see here. We call this a pouch cell at the end. They hold about, give or take, the same amount of energy as an iPhone battery does. And so we make those, we have to put them together, and then that tells us about do we have something that's actually viable in the real world. And so last year, the answer to that question became yes, and now we're starting to look at, well, what's next? And Maria mentioned Battery Hub. That's one of the things that we can start to do in Victoria, is putting those tools in place to make it easier for things to come out. This pouch cell we made, one of the questions we wanted to answer was, well, how safe is it? In order to do that, you put it in a test facility. There isn't one here. So it'd be good to put it on a plane. I can't put it on a plane because it's a battery. So I have to get a certificate to put it on a plane. The only place I can get that is in the UK. So my battery went on a boat. It took a year to get there because I had to wait for a ship captain to put it on the boat, right? Because it's an emerging area. Now, if we had that ability locally, I would have just saved a year by doing that. And they just started testing them this morning, actually. So I can't tell you how they're working, but they're there at the moment. So then what does it take to go through this? There are a number of steps, and it's kind of emerging as to what the steps are to do this, and maybe relevant to us here in Melbourne. We're very good at biomedical research, and you probably hear about clinical trials, and if you think of the COVID vaccine, we're all experts at what stage of approvals these things are at. Batteries have kind of got the similar sort of steps that we look at, and this reference I've got here talks about this, of saying, hang on, if we think of the pharma industry, maybe we can be more efficient at getting this energy storage technology out there. So where we are now is we're developing this pouch cell. We're going to give it to Maria. She's going to test it independently and then tell us if it does what we say that it does, and that becomes important information that we can take. So it's great that we have that facility there. So that's enough from me. I'll leave with our beautiful pictures of ourselves standing around pretending to look at batteries, and we'll be happy to answer any questions. Thanks very much.
Thank you, Matthew. And we now have some time for questions, so start thinking about those questions. Do we have a microphone? Yep. So I'm going to kick off with a question, though. You've both mentioned gigafactories, noting Victoria's strong tradition in manufacturing. What's the potential for us to have a gigafactory here in Victoria, and what are the skills or the training needs we need to have one of those?
I guess I'll start by saying I question whether we need to have a gigafactory as opposed to distributed manufacturing of lots of hundreds of megawatt-hour factories, which are more flexible as well. But could we have a gigafactory? Yes, we could. It would take $1 billion to set it up, at least, minimum. And that's part of the problem, is cost. And you'd have to have investors who want to come here and do that and put that money in. And people did try here, but we haven't succeeded yet. Do we have the skill set? Nowhere in the world has enough skills yet. There's going to be millions of people required for this transition, so we need to actually be looking at developing that now. And there are things all of us are doing, but we need to be really looking at training, both at the TAFE level, in the schools, at universities. Engineers have to start looking at the future jobs that we'll need for being able to build and sustain and fix batteries, etc. Lots of things like that need to be done. So yes, I think we can, but I would say hundreds of megawatt hours rather than lots of gigawatt. Exactly. So did you want to?
No, that's fine.
Did you want to?
No, you don't.
Most of that went completely over my head. But you said 11.4 thousand terawatt hours to do what we currently do now with electricity. Is that what you were saying?
2040.
By 2040.
So, yeah.
So when I see in my part of the world a battery proposed, and I'm picturing a great big car-looking battery about the size of a bedroom, yeah. That's literally what I probably am thinking of. No idea, no vision, no concept. How long, if that has any size relevance to the reality of life, how long would that last for when the power went out for a town like Warrnambool that's 35,000 people?
It depends on the battery is the answer to that. So if you
give me an idea.
No, that wasn't supposed to be a joke, but lithium-ion batteries are very good for fast response and for 1 or 2 hours. Well, it depends how many batteries you put in there, I suppose, but for about maximum I've seen, I think, is about 4 hours that will last if you have a power failure.
Cost to get a 4-hour battery for $35,000.
Well, how much that one? I don't think what it costs. I should know that number, but I don't off the top of my head. It'd be millions.
Yeah.
Be millions, right? But there are other batteries, the vanadium flow, the iron flow, and metal air actually that are proposed that have been shown to last for 8 hours plus, right? So if you want to put something near a grid, you're actually better off using some of the other flow batteries, other battery chemistries that exist. At the moment, they cost more because there aren't gigafactories making them. So we need to be making now in WA, the Vanadium Australia is making a vanadium electrolyte. They can start making vanadium flow ultimately. Queensland's just announced another vanadium flow battery manufacturing plant for here. There's iron flow being built in Victoria and also in Queensland. So it depends on the battery and where you want to put it.
I ran a dairy farm for many, many years. 4 hours. Sorry, not very helpful.
No.
How far are we away from me as a dairy farmer going, great, we got lines on the ground that are going to take 7 days. Cows are going to be very sick and dead by then. How far away are we from getting a system that will give me 7 days, 2 weeks of power?
That would not be a battery in my view, but not for 7 days.
Well, yeah, so the short answer is that we don't know, but when people ask how long does it take to bring something to market, the real answer is, well, how fast are we going to try to go? So if I do this on my own, it could be 100 years. If we make a major effort, it might be 2 or 3 years. Now, when you talk about the batteries, a lithium-ion battery for 1 kilowatt hour of energy, let's call it, it's about $100 for that. These flow batteries might be $1 if we get them right. That's the potential that we could have. So they could be basically meaningless in terms of the cost of doing things. And then that just means everyone reimagines everything when the battery's just there like that.
And just to finish that one, actually, sorry, to finish that before you said 7 days. Well, you're not going to be using the battery for 7 days. You're going to be using solar and wind, and then you'll be using the battery when you haven't got solar and wind. So you're using it as backup storage. You're not using it to supply all your electricity.
But I've had cows die because I didn't have any wind for 10 days, and seriously, the windmills didn't do it. So what do you do when you don't have the wind? So if you've got some sun, let's hope those can...
And that's where the potential of hydrogen also comes in as well, right? That's not a battery. That's a different technology. I won't go there.
No. Just while we're getting ready for that question, I might ask another one, and I think it's one that's relevant. Safety is an obvious issue. There was a mention earlier on of fires, and we're all aware that lithium-ion batteries can cause fires. Can you talk a little bit about how some of those issues might be avoided in the future?
I guess we both are working on technologies that are safer. The reason we have fires is because the materials that we have in the battery are flammable or very highly energetic. So the organic solvents which catch fire, we're working on systems which are molten salts effectively, but room temperature, which are not volatile, do not catch fire. Sulphur is more stable, for example, than the NMC, doesn't have thermal runaway. So we're building technologies already that are safer. Would you...
I would agree, and I was driving home on the Monash just before Christmas, and there was a fire 20 metres high on the side of the road, and I didn't even make the news because it was just a regular car. And if there's one stat to take home with you, even today, electric vehicles catch on fire less often than combustion vehicles. So the news is the other way around. Maria's right, there's a lot more to do, but we're already ahead. Now, it is new and scary, like any new technology, but that's just a reality. That's just a fact to take away. There's a lot of hesitance about battery storage, and it is, any storage of energy has that can be released in a way we don't want, but it is much safer than combustion engines even today as a new tech.
Well, my question was along the same lines, but can I just clarify? So the battery fires that we see in bicycles, and not allowed to put them in apartment blocks in overseas and all those sort of things, that's the lithium ion versus lithium sulfur.
No. It's lithium.
Well, mainly yes, and what happens is there's oxygen inside the lithium-ion battery, and so when something goes wrong, oxygen is what makes a fire burn, right? That's the air, but it's already in there, so it can keep going. But a lot of these other batteries, there's no oxygen in there, so it can't do that. It's not possible. So that's where we're headed with a lot of these things. Yeah.
Can I also comment that the reason we're seeing a lot of these fires is because as you build more and more gigafactories and the quality control is not carefully taken care of, then those batteries become are not. They don't perform the way they should. So companies like LG and others have had to draw their batteries away because basically it was quality control. So you can, it's not just about all batteries will catch fire. If you handle them properly and if they're properly made, then the risk, as you said before, the risk is not so high. But as you flood the market with lots of cheaper imports, that's where you've got to be a bit more concerned, I think. But inevitably we will get to a safer battery. That's what we're trying to work towards. But the current ones are not super dangerous. It's just that it depends on the quality control and how you treat them.
There's a question here.
Yeah, I think this research is really fascinating, so this is a very enjoyable speech. You talked earlier about how the regulatory environment can be an obstacle, and I was just curious as to whether there were further regulations, particularly, say, in Victoria, that are a hindrance to you accelerating your work. And I guess there's a sub-question in that. Things like the nuclear moratoriums that prevent sodium mining and other mineral salts mining, is that relevant at all to this discussion?
You know much about the regulation? I mean, what I know about the regulations, the standards are a problem at the moment. The standards need to be worked on better. At the moment, they're all around lithium, and that's a problem. And I think where the problem comes is not that people like Nation Energy are selling their battery, or they're trying to sell their battery into the market, and they are placing it, and they can do that, but they can't get approval from the CEC, for example. They can't get accreditation because they don't meet the standards. So that has to change. With respect to mining, I don't know, I haven't got an answer. I'm not sure about that. But I think in general, as we start to use more and more batteries in more and more applications, and safety becomes an issue, the standards and regulations have to be really carefully, need to be looked at. But I think.
Please go ahead.
No, if you've got more.
I was just going to say, in general, this is clean tech manufacturing. So there's these germane challenges of it's a long time. You've got to build a factory. You've got to have the right legislative environment that the risk will be taken by investors. Right now, we're seeing some of these things be built not in Victoria at the moment, and that's probably telling us where the most favourable legislative environments are.
Apologies, I missed the first couple of minutes, so you may have covered this, but Toyota's announcement about solid-state batteries, where do you see that going? Is it the revolution in EVs in particular that we're looking for?
I know the guys there, so we work with Toyota on different parts of solid-state batteries. Look, they're not the only ones doing solid-state batteries. Solid-state batteries are safer intrinsically than liquid electrolyte batteries. And they use lithium metal, which means a higher energy density, so that means they can go further as well, and they can be faster, more rapidly charged. There's a lot of announcements out there. This is another one of those. I mean, I know that they're doing it. I know there's a lot of limitations still with that technology that they are working towards, so increasing the cycle life of a battery. The life of a car needs lots of cycles of a battery. Is it the revolution? I think a lot of people are working on solid-state lithium batteries around the world, like other battery technologies. Will it be the one that ends up being the only technology? No, it'll be one of the technologies for certain range of vehicles. Sodium will be in small cars, I hope, should be, it's cheaper. Lithium itself will be on long-range haulage trucks because it goes further, I think. Solid-state lithium will be in your high-end high-end Teslas, or those cars that want to go much further, much faster, etc. So there'll be lots of different types of technologies. I just think. I think that's true. That's what people...
Yeah, we're sort of deep into the hype cycle of any new technology, and generally what we see is that they're great, but nothing's ever a silver bullet. And that's the way we can think here is, we can pick a niche in this country and this city to focus on, because that's always going to be true. We're not going to be just competing against some Chinese factory that makes every battery on the planet. It's just not going to happen. There's a family of technologies and they're embodied in products, and we can focus on things that are where we have that natural advantage right here.
While the microphone's being moved around, I'll ask another question, and I think you sort of touched on this, but who do you think are the leaders both within Australia and globally in this space? How does Victoria compete in this space, and who are the main competitors, if you like?
Okay, leaders in terms of making and selling, China. Right, CATL, BYD, even in the sodium world, when I was there last year, there's 100 new startups. Not all of them will succeed, but there's 100 new startups in one technology. So they just have the people and the money, and so they're in terms of making. In terms of technology, I think Australia, I know Australia is in the top 5 or 6 in terms of new technologies. I know that because I gave a talk to the National Science Council and I saw the stats, and actually we have a number of top scientists in Victoria and Australia working in these next generation technologies. So I think if we choose to go down the path of commercialising some of the things we're actually innovating, then I think we could be leaders in certain areas. I won't call them niche. Niche sounds too small. Not 11.6 terawatt hours, but more specific areas specific to Victoria and Australia. Would you agree?
And what are those areas, Matthew?
What are the areas that are specific? Yeah. Well, I think we could go beyond just that you're making a battery, you're making a product that has a battery in it that works. And so for us here in Australia, we need to be thinking about perhaps those larger vehicles here, and we used to be a proud automotive state here. That doesn't have to end. We can focus in large vehicles in particular, as you mentioned, trucks, fleet vehicles. These are things that there's a huge natural advantage to have with this. But also the other thing, what do we have here? The highest rate of PV on the roof in the world. We have a grid that's going to get to the point it can't have us all putting our solar power in on a day like today. So storing it at home is another one where we have a huge natural advantage.
And that's where sodium-ion batteries actually probably have an advantage too.
Is the microphone gone? We've time for more questions from the audience. There's 2 more hands going up now. Yep.
Hi, just wondering about the comparative weight of both lithium sulfur bats and sodium ion bats in comparison to, say, a lithium solid state, and whether that is going to enable them to be utilised in other commercial capacities, such as, power drills and things like that.
Okay, so Tiamat, the company who I showed, the French company, their first product is a high performance, fast charge power drill. That's what we're selling at the moment. So because sodium actually also is much good for high power. Weight advantage. So lithium batteries have copper and aluminium as your current collectors in the battery. Sodium batteries have aluminium and aluminium. Aluminium is lighter than copper, so you gain back some of what you've lost because sodium is a bigger, heavier element. In the case of lithium sulfur, you don't actually even use a current collector necessarily, just use lithium, which is the lightest out of all the metals, right? So I couldn't give you the numbers, but I can tell you that it's on par. By the time you make from the cell to the module to the pack, you're on par.
There was a question over here somewhere. Yeah.
Thank you. So you've talked a little bit about city cars versus long distance versus trucks and things like that. I'm wondering where sort of e-bikes and mobility, what kind of technologies are going to be best suited to that kind of environment?
I think the really small cars, so I mentioned my colleague Mainak, who's Indian, and he's there right now, and he cannot stop talking about tuk-tuks in India and that they need to, and what's the number one thing there? Cost, right? It needs to be really cheap. And so I think things like sodium ion are very attractive because the materials in there are so cheap for that. So probably those sort of batteries. But I suppose the message we're saying is there's probably 5 batteries, maybe even 10 batteries that are what we need, and they're each finding their niche. Bigger than a niche as we go along.
It's niche, but it will be a big niche.
A big niche.
We have time for 1 or 2 more questions. Do we have more questions in the audience? While you're thinking of a question, you've both talked about sustainability and you've talked about how the metals play into this space. What are the other components to the battery that we need to consider, both in terms of supply chain management and also then the recycling, the disposal issues?
Yeah, recycling of the battery is crucial. If you do the maths today, in Melbourne, the best thing to do with an old electric car is leave it in your driveway and plug it into the grid, not to actually reuse the battery materials. This is a really hot area of research about how do you take the metals back out in a way that's not expensive and dirty and then use them again. And we don't really have much of a solution right now. It's a really important thing.
We do. Sorry, just on that though, we do have a bit of a solution because we can actually take the batteries that come out of the cars, and there are 2 companies in Victoria that are doing this. It's Innovative and these are they're actually taking the batteries out and then they're repurposing them for stationary energy storage. So Infinitive and Re-Electrify. So that's the first thing you do, is you repurpose and then you find ways to recycle.
Yep. Can you comment on that point, though? There's more than just the metals.
Sorry, yes, there is. I should say that the EU, at the moment, the current lithium-ion batteries use PVDF, which is a fluorinated PFAS, basically polymer, and that you can't dissolve that in water. You have to use nasty solvents. So people are working very hard, including ourselves, on aqueous based polymers that can be actually dissolved in water, which makes recycling easier and gets rid of the PFAS as well.
Yeah. Although, sorry, this is a little bit more area. You won't necessarily make PFAS out of PVDF, but you will make a fluorinated chemical. So before you frighten everybody too much. Do we have any more questions? We have a couple more minutes, so I'm just going to perhaps pass to these guys, see if they want to make any concluding comments before I wind up. You don't have to, because I've run out of questions.
I guess the message you want to get across is what we've been saying, is that we do have opportunities in Victoria, in Australia, but in Victoria, to be part of this transition. At the moment, I feel like we're sort of missing the boat a little bit. We were a proud manufacturing state, and we don't manufacture so much anymore, but there's an opportunity here. We have fantastic scientists, innovation, but Matthew's going to a company, we're starting a company as well. We want to take our work into the real world, but we also have to have both government support and venture capital is a problem in this country, but maybe regulations that help, or policies that help people invest in companies to be able to make that transition. So that's something I think is really important. Victoria seems to be a bit behind on that, I think.
Yeah, probably maybe the sunny side up would be to say we are so good at this technology in this state. So we have, the research here is world leading that we have. It's devastating when we see it go overseas. And Maria probably had the same as me. I've had the phone calls, could we buy your tech and put it in China? It would be better, we would make more money, but we said no, because we're a bit parochial. But not everyone can be as silly as that. So it's right there. We've got a huge advantage. We've just got to try and catalyse that.
Thank you, and we will try and finish up there. So I'd like to formally thank both our speakers, Maria and Matthew, for what I think has been a very thought-provoking presentation. Note that both speakers are happy to be followed up on any of the issues that they've covered. You can chat to them immediately afterwards, but otherwise they can be contacted via the library, so please feel free to reach out. Just letting you know that our next Science and Technology lunchtime presentation will be on curbing microbial resistance, and that'll be on the 30th of May. So otherwise, I'd like to thank you for your attendance and hope you enjoyed today's presentation. Thank you.